at University Complutense of Madrid, Spain. And I'm one of the co-authors of these materials that we're going to work with today. With me, it's Yiting Chen and Jingjiang Liu. They both work for Imagination, and they will help us during the workshop. And also, Robert Owen will join us later. He's the manager of the Imagination University program. So, well, first of all, you should all have received an email from us with the instructions for the preparation of the workshop. You should have registered for the University Program of Imagination Technologies, request the RVfpga package version 2.2, and install the software as described in the installation guide. If you have done that, great. And if you haven't, please do it as soon as possible so that you can work on the hands-on exercises later. You should all have a board, a workshop guide, and a USB flash drive. If any of you don't, let me know. And you should please copy what's in the USB flash drive. It's a folder called Workshop at Imperial, and it contains several resources for using today. Specifically, it contains an RVfpga package, the same that you downloaded, except for some minor additions that we'll use today. So it's important that you use the RVfpga package provided in the flash drive, okay? And please place it in a route, in a path that contains no spaces. Otherwise, you can have trouble later, okay? Finally, please fill the survey before leaving. We'll provide you a link, and it's very important for us to receive your feedback, your opinion about the workshop, the materials, your proposals for improvements, whatever you want to mention there. Okay? So there are many persons we have to acknowledge, first of all. All of them are listed here. And also several companies who sponsor and support these materials, mainly Imagination, but also others such as Western Digital, Chips Alliance, RISC-V itself, and Platform.io, and many others. RISC-V FPGA, or RVfpga, is a course that shows how to target a commercial RISC-V core and a system on chip to an FPGA and to a simulator. We'll use both of them today. It shows how to program the SoC, both in C and RISC-V assembly language. It shows how to add functionality to the SoC, such as new peripherals, new instructions to the core, and some other things. You think? Yeah. Sure. Okay, thank you. And also how to analyze and modify the RISC-V core and memory hierarchy in the last labs. The package is being developed by Imagination Technologies and its academic and industry partners. And after completing the course, users should be able to work with a commercial RISC-V processor, SoC, and ecosystem, understand it, and be able even to modify it. Imagination Technologies offers two courses based on the RISC-V architecture. RVfpga, which is the course covered in today's workshop, and also RVfpga SoC, which is a second course that shows how to build a RISC-V SoC from building blocks, install Zephyr real-time operating system on it, run programs on Zephyr, and also run TensorFlow programs. We won't cover these materials today. We will only cover the first course, but the second one is also available for download if you're interested. Both courses are available in this webpage, University Program from Imagination. So the target audience of this course is mainly undergraduates and master students in electrical engineering, computer science, or computer engineering, but also academics and industry professionals who are interested in learning the RISC-V architecture. Well, Imagination University program developed MIPS FPGA program some years ago. It was launched in April 2015. It was engaged by more than 800 universities, and it was the winner of the Educational Support Award called Electra in 2015. Well, let's take a brief course overview. So this is typically a 2 to 3 semester course. Labs 1 to 10 are mainly for undergraduate students. Labs 11 to 20 are more advanced, so more targeted to master's or upper level division students. There's some expected prior knowledge, such as some concepts of digital design, high-level programming, preferably C, instruction set architecture and assembly programming, microarchitecture, memory systems, and all these topics are expanded when doing the RVfpga course. And in fact, these are the topics covered in the recommended textbook, which is the one written by Sarah Harris and David Harris. Sarah Harris is one of the co-authors of these materials. And this is the book we recommend. Obviously, the Patterson and Hennessy book is also fine. As for the required software and hardware, you will need Vivado, not in this workshop, because we'll provide all the bit streams that you'll use. But in case you want to build the SOC on your own, or you want to modify it and rebuild it, you'll need Vivado. Okay? Any version should be fine. We're using this one, but any newer versions should also work. And also, you need Platform.io IDE, which is an extension of Visual Studio Code, which you should all have installed yet. And it includes Chips Alliance platform, which includes the RISC-V toolchain, OpenOCD, Verilator, which is the HDL simulator that we'll use today, and Whisper, which is an instruction set simulator that we'll also use, Verilator, and GTK Wave. As for the hardware, in addition to your laptop, you should use the Digilens Nexys A7 board that we've provided. But, well, we say that this is optional because all labs, or most of the exercises in the labs, could be done in simulation. So it's better to have the experience of using the board. But if you don't have it, you could also use only simulation. We use the Western Digital Swerve EH1 core, which we'll analyze later in high detail. And the SoC that we use is built around this core and is called Swervolve. Both of them are open source. And they are provided as part of the RVfpga package that you've downloaded and that you've copied. This is the board we're going to use, Nexys A7, which is the successor of Nexys 4 DDR. Probably most of you have a Nexys 4 DDR. It's perfectly OK. It contains an Arctic 7 FPGA. It includes many peripherals, such as LEDs, switches, push buttons, 7-second displays, accelerometer. Most of these we are able to use them in RVfpga. And let me say that we will soon support the Basis 3 FPGA board. In fact, it already works there, and I'll show you a demo at the end. And we'll release it soon. And we also plan to provide support for other boards, such as Intel boards or others. It supports all 3 main operating systems, Ubuntu, Windows 10, and Mac OS. Well, what's the system that we use in RVfpga? It's an extension of Chips Alliance's Swervolve SoC, which is based on the Swerve EH1 core developed by Western Digital. As I said, all is open source. So this is a diagram of the RVfpga system. It includes the SwearVH1 core complex, which has the SwearVH1 core plus some other elements, such as scratch pad for instructions and data, instruction catch. All these elements are inspected in the course. Around it, there's the SwearWolf SoC, system on chip, which includes many peripherals, such as GPIO for using the LEDs and the switches on the board, a timer, well, a boot ROM, support for the 7-segment displays, and other things. And this can be targeted to the board in what we call RVfpga Nexys, or to a simulator in what we call RVfpga Sim. So in the next slides, there are some more detailed figures about all this system. So this is the core complex. It includes the SwearVH1 core, which is a 32-bit superscalar core with a dual issue 9-stage pipeline. It has separate instruction and data memories, scratchpad memories tightly coupled to the core. It includes a 4-way set associative I catch. It doesn't include a data catch. It has an intercontroller, a debug unit compliant with the RISC-V debug specification, and it supports both AXI4 and EHB Lite. We'll use the first one, AXI4. As for the SwearWolf SoC, it is based on the SwearVH1 core complex. It adds interconnection. It has the AXI4 interconnect with a bridge for the Wishbone interconnect, Wishbone bus, which is the one used by our peripherals. Okay? The peripherals that we use are downloaded from OpenCores, and they use the Wishbone bus. So we need to convert between both buses. Here you have the memory map for the peripherals included in our system. And this is a figure of the RVfpga Nexys. It includes the SwearWolf SoC, plus a clock generator, some logic for the JTAG, a lead DRAM controller that allows us to use the external memory available on the board, and, well, the peripherals from the board. Also, the RVfpga Sim allows us to test everything in simulation, specifically in Verilator, as you'll see later. In labs 6 to 10, we extend the basic SoC with support for other peripherals, such as the push buttons available on the board. We include a new controller for the 7-segment displays in order to be able to show any combination of on and off LEDs. Also, we include new timer modules that allow us to work with the tricolor LEDs through PWM, and also new external interrupt sources. We'll check this in detail, and you'll even check on the board some of this. Well, let's give a brief introduction to the lab's overview that we'll cover in this workshop. So we've divided in 4 parts. First part is about programming. So lab 1 is about C programming, lab 2 about RISC-V assembly language programming. Lab 3 works with function calls. And lab 4 includes a big project about image processing, which combines both C and assembly languages in the same project. We'll do a demo later on lab 4. The second part is about input, output, and peripherals. So lab 5 shows how to create a Vivado project and create the bit stream that we are providing you, but that you can generate following the steps in lab 5. In lab 6, we give an introduction to input-output based on GPIO and communicating with the switches and LEDs. Lab 7 works with the 7-segment displays on the board. Lab 8 works with timers. In Lab 9, we work with interrupt-driven input-outputs. In the previous labs, we work with polling input-output. And finally, in Lab 10, we work with some serial buses, the most common serial buses, SPI, UART, and I2C. Third part starts with microarchitecture, introduction, main concepts, main basic concepts. So in Lab 11, we give an introduction to the SwearVH1 configuration and organization. And also we show how to use performance monitoring available in this processor. Lab 12 shows arithmetic logic instructions, how they are executed in this processor. And we do a detailed example with an add instruction. In Lab 13, we introduce memory instructions. We work with the load and store word instructions. And Labs 14, 15, and 16 work about hazards, structural, data, and control hazards. And in Lab 16, we also show how the branch if equal conditional instruction is executed in the pipeline. Finally, part 4 is about advanced features and memory hierarchy. So we explore superscalar execution in Lab 17. We show and ask students to add new instructions and other features such as hardware counters to the original core. So they will have to add those instructions and test them in their own programs. And then Labs 19 and 20 are about the memory hierarchy. So we first analyze and test the instruction cache in the core, and then the scratch pads, instruction and data scratch pads, and also some concepts and some exercises about benchmarking. In the RVfpga folder that you've downloaded and that you've copied from the flash drives, you will find several subfolders. One is called Documents. It contains several documents. The main one is the Getting Started Guide, which are the initial instructions and examples to use RVfpga. This is the first document that you should do. It's an extensive document. You will also find the slides, the workshop guide. This is not the same workshop guide we're using today. You have the workshop guide we're using today in the printed document that we've provided, and also in the folder that you've copied. There's also another subfolder, Verilator Sim, which contains the sources for the Verilator simulator. Folder SRC contains the Verilog sources for the SOC. This is what you'll include in the Vivado project in case you're building the SOC, and which you'll have to modify in case you want to add new features. Subfolder examples contains some Platform IO projects for the GSG examples, for the Getting Started Guide examples. We'll do now some of them. And finally, the Labs folder contains 20 subfolders named Lab 1 to Lab 20, each one for each of the 20 labs that we have, with instructions, figures, and resources to be used in each of the labs. So in each of these subfolders, you should find a document for that lab describing everything, including all the exercises and so forth. And there's another subfolder called RVfpga Lab Solutions, which contains exercise solutions for all the labs. So we're providing all the solutions for everything we're including here. Not only the programs in C or assembly that are the solutions for the exercises, but also modified versions of the RVfpga system, including the new peripherals that we ask users to include in the different exercises. Okay? We'll use some of these today. So let's start with the first hands-on activity. So let's start with some of the examples included in the Getting Started Guide. These are the 3 examples that you should test. Let's switch example first, execution on the board, following the instructions in the workshop guide, the first section that you'll find there. Then hello world example, which prints a message on the console. And then you'll simulate, the first 2 are on the board, are executed on the board, and this one will be executed in Whisper and very later. Finally, if we still have time, you can take a look to the Getting Started guide and test some other things you're interested in. So for the first one, let me do a demo. At the same time, you can be working on your laptop, but given that it's the first one, I think it's good that we do it together. So you should open the VS Code. First thing is to open the folder that contains the example, which is located in the RVfpga folder. Remember to use the one that you've copied from the pen drive. And it's in examples. Let's switch it C-lang. Let's use the one programmed in C language, okay? So click there and do not select anything, but just click OK. The example should open in Platform.io. Platform.io should start. It may take a few seconds. Okay, now it's started. It's here. If you click here in Platform.io, you have all the options. That one of them is to upload the bit stream on the board, for example. If you click here on the Explorer and you open the platform.io.ini, this is the configuration file for the project. It includes the path for the bit stream that we want to use. Okay, we're going to use this bit stream located inside the src folder. This is prepared. This should work as it is. Okay, you don't have to change anything. I'm just showing so that you know that this is the configuration file and this is the path for the bit stream. But please don't change anything. So if we click upload bit stream, the bit stream indicated here should be uploaded on the board. You will see how it changes. You will see how this flashes, and that's the boot program included in the boot ROM, and then it stops there and waits for us to execute the program. So the program that will execute, you can view it again in the Explorer. If you open the src folder and you edit this file, you'll see the program that will run. It's not necessary that you understand everything here because we'll go back later. But this just stays in an infinite loop which reads the switches and shows the value on the LEDs. Okay? So for running the program, you click on Run and Debug here and here, okay, and the green button on the top. When you do this, program is downloaded and starts executing. It stops here. So if we continue running, but we have the controls here, you can just continue the program. It should be running here. So if you switch any of the switches, you invert any of the switches, this should be reflected in the LEDs. Okay? So please try this program on your boards and let me know if there's any problem.